I think it was probably initially covered in either intermediate algebra or college algebra. So some of you might have known that, some of you might have forgotten, or some of you might have never seen it. Okay, so I will do my best to make sure everybody understands. And for that matter, in terms of the, yesterday we talked about the these relationship, right? These relationship. We have one function, right? And it's one function. So I'm going to bring this to the top. Okay, we talk about this is the only function that has the function and its inverse are exactly the same. Okay, so recap. Okay, recap from yesterday that we talked about the one-to-one function, right? The example we talked about was this one-to-one function and its inverse. Its inverse, right? And then we went about to write these, okay? For those of you who are not quite familiar, or I'm gonna do this again, and today you're gonna have, well, I didn't give you homework yesterday, and today you're gonna have some homework. Okay, so what happened is that we talk about function, right? Function that you have an input, it produces an output, and this input will be served as another input for the next rule if this input happens to be in the domain of the next rule. And this is how we express it. This is how we express it. Okay, so if you think about it, you take a mathematical notation, math notation. Okay, math notation to express this process. And of course, will be this one, right? Will be this one. What it does is that, okay, so let me write it down. We have one input and we apply our function, which is a rule of the function, a rule of a function, and that's the output. Okay, so see, this is input and that whole thing is output because after the rule has been applied to it, and this is the output. And this output serves as input for the next rule. The next rule is F inverse. So this is going to be served as an input. Okay, this is served as input. And the next rule is going to be F of inverse. It could totally be a different rule. Okay, and this is going to be the same as the input that we start with. So this is the output after the second rule applied to that input, and the output will be exactly the same. If, of course, there's a big if this function is one-to-one and this x is in the domain of F. Are you guys with me? Okay, so one more time. If this function this inverse function apply to an input which is in the domain of F inverse, okay? So we have an input, and this input is from the domain of F inverse. And we're going to apply the rule of the function F inverse to it. So we produces an output. So this is the input, and that's the output, which describes this piece. Now, this piece is served as input. This is served as input again to another rule, and this rule is called F. It produces the output of such, which is going to be exactly the same as input. And of course, conditional, only when this is the function that has inverse. Okay, It's one-to-one. You guys follow me? With the specified domain and range, as we talked about yesterday. Do you guys have any questions? Okay, so now I'm going to put some notes here. Okay, yesterday we mentioned this. This X is in the domain of F, because this X is first being taken as input by F. So it must be in the domain of F. Okay, this X, however, is in the domain of F inverse, because X is first served as input for F inverse. Does everybody follow me? And this is probably something you have seen before, okay? And this process, okay, this entire process is called composition. Composite function, okay? I call it composition of functions. Compositional functions. And of course, we are discussing a special case. We're discussing a special case. I just want to check, make sure the door is closed. Okay, this is the special case. So what will be the general case? Okay, so let's review a little bit of the general case. You have seen this before. You have seen this before. Have you guys seen this notation? F composite G. Has any one of you seen this before? Has any one of you seen this before?
Yes, hope so.
Is Farouz the only one who's seen it before?
I have not, no.
Huh?
I don't remember seeing it anywhere.
I have.
Okay, some of you have not. Okay, some of you have not. That's fine, okay? So compositional function is saying that, okay, I have, we got some people seen it, some people have not, which is fine, okay? You're gonna see compositional functions in calculus immensely, a lot of it, okay? So what is a compositional function? When we talk about functions, so now how many functions we have so far? From the basic table. 1, 2, 3, 4, 5, 7, 6, 7, 8, 9, 10, 11. Well, we only have done 9, 11, 13, right? So that's a total of 11 functions, right? That's a total of 11 functions so far. We have 11 functions. Okay. So do you have those 11 functions with you? You should have basic one table in front of you, right? Before we review the composition or introduce this again for some of you introduce it for the first time, imagine all of these functions being added, subtracted, multiplied, divided, and in addition to adding, subtracting, multiplying, dividing, what do we get? Okay, so let me write down all these 11 functions, okay? I'm gonna get those tables, okay? Could you guys get those tables for yourself? We're gonna do something fun at the beginning, okay? We're gonna do something fun at the beginning, okay? I promise you, it's not gonna be terribly hard, okay? These functions. It's a little bit difficult to do a copy and paste, but that's what I'm going to do. Okay, copy and paste. So give you a little perspective. Okay, so I'm going to copy one at a time. Okay, so I'm going to copy this table. Okay. And this table, we're going to do a little bit like a magic show. Okay, a sort of a magic show. Right, all these functions we have just reviewed, right, or studied. We know their domain, range, x-intercept, y-intercept. For some of them have no inverse. So what we did, the f of f inverse, we don't do that to them. We only do functions, only work with functions with inverse, and they do similar operations like this. Okay, only for function that has inverse. Okay, only for function has inverse. X belongs to domain of, let me write it down. I need to complete the sentence. Okay, X belongs to the domain of, domain of that. Okay, so make it complete. Now, with that said and done, I want to review the operation about this. Okay, review the operation with you about this. Okay, what I meant is that, can you imagine all of these functions? Okay, this guy, this guy, this guy, for all the way up to, we have 8, 9, 10, 11, 12, right? 13, 14, whatever, however you count them, you can create very many, you can create more. Okay, take an example. 11 functions or 14 functions, whatever you call them, right? What you can do is that if you add them, you add up, you choose any two functions, you add them. For example, if I add constant c with x, sorry. Okay, suppose I take this functions c, okay, constant c, I'm adding with x. Okay, what happens if you do x plus c? Right, that's adding functions, right? So one function adding another, any one function you add another function. Okay, example, you have created a new function. This new function is a special case of what? Mx plus b. You follow me?
Linear function.
That's a linear function. That's an example of linear function. And I can totally make a multiplication of m times x plus c. And I can very well make it b. Okay, so the symbol really doesn't matter, right? So when we have these basic functions, we can add them and create new functions, and that's a linear function. And another example I can do is that I can do ax squared plus bx plus c. Can I do that? Right? What is x squared? Here's x squared. I multiply x squared with a constant, and a plus b with x, right? With x. Wait, where's x? Where's the x function? It was somewhere here, right? Right here, right? And the constant. I created, what do you call this? Quadratic, right? Quadratic function. We're going to address it again. And in similar way, we have an x cubed, right? So you can totally make like k times x cubed. K times x cubed plus ax plus bx plus c. You are creating polynomials. Okay, just by adding, subtracting, right? You'll be creating new functions. Don't these functions look familiar to you? You have seen them in elementary algebra, intermediate algebra, right? So by adding, subtracting, we created more functions from basic functions. How about multiplication? How about multiplication of functions, right? F of x multiply g of x. What will happen? Let's look at some examples. Okay, this is the magic show. Okay. If I multiply x with x squared, multiply with x raised to the power 3, what have we created? We have created x raised to the power 6. Another new function. And all of these, from adding, subtracting, multiplication, division, we can create function as complicated as possible. And I haven't mentioned the exponential functions being part of it. Okay, you can create as many functions as you wish. Now let's see how about division. These are the functions you have seen in your algebra classes. And of course, they could come with more complicated shapes and forms. Division, dividing. Okay, one function divide by another function in its various shapes and forms. And you're going to see all of these and its many variations in calculus. In calculus courses, plural. Okay, so example, right? Dividing. And of course, when we divide it, we need to make sure the denominator cannot be what? Cannot be what?
Denominator cannot be 0.
That's right, cannot be 0. So now I hope you understand why we study the basic functions, right? Because from basic function, we create infinite number of functions. Okay, now dividing, example of dividing, right? For example, I can take this guy, divided by this guy, right? You create new functions. Another example, right? I'm just going to give you a concrete example. And this time I'm going to have x squared plus 5x plus 6. Okay, 5x. I'm just doing it randomly, okay? X minus 2. This is a b. You follow me? Those are new functions you can create. Those are the new functions you can create. Adding, subtracting, multiplying, dividing, we can create numerous functions. And now we talk about composite functions, composition, right? Some of you have seen it. And this is also very, very useful, very, very much used in calculus class, is a composite function. Okay, how is this defined? F of g of x. That's what it is. That's what it is. Okay. In all of the above examples, I'm not going to spend too much time there. Okay, because the essential ideas probably is just x is the input, and the input go to any way you created the function. Okay, any way you created the function. Okay, you may have a f plus, you may have this, this is going to be a new rule, and this is going to be a new rule, and this is going to be a new rule. Okay, these are the new rules. Okay, so let me do this. Copy.
So, in general, we can call it operation on functions, Professor.
Yep, operations on functions. So this is adding, so I'm going to make a subtracting, right? So with all these operations, and you create new functions. Do you guys see that? Look at the definition of function again. Look at the function definition again. Once we have those basic functions, we adding, subtracting, multiplying, dividing, we create infinite number of new functions. So we're going to get a bunch of different outputs, and they're also unique. They're also unique. Okay, it's guaranteed. The next one, which is very special, is the composition. It's like composing music. It's like composing music. We have a composite functions. Okay, that's why I like to call them compositional functions. Compositional function is even more versatile. Okay, so let's look at a couple examples. So hopefully it will remind you of those, what you have learned before. For example, I may have f of x equals to x squared. Okay, g of x equals to what? Equals to 2x minus 1. How about that? Right? So what I'm going to do is I'm going to do f of composite g of x. What would that do? Right? It's f of g of x. You always do from inside first, right? From inside first. This quantity, x, they should be viewed as a placeholder. You guys understand what's a placeholder? It holds a place. It holds a place. So when I do g of x, right, I will do directly f of 2x minus 2. 2x minus 1, sorry, 2x minus 1. So I substituted g of x by 2x minus 1. Now, what is f of 2x minus 1? F of 2x minus 1 is here. See, this is the rule for f. Okay, when I substitute x by 2x minus 2, this x will also be substituted by 2x minus 2. Does everybody follow me? Does everybody follow me?
Yeah.
You must do it on your paper. You must do it on your paper, okay? Now, so as a result, I will get a new function as a result of a composition. Composite G. So let's look at G composite F. G composite F. Does this look familiar to you guys? Yes? Yes or no? Please remember, yesterday I addressed you must ask questions. You must ask questions. If you don't ask questions, I assume you don't have a question. Okay? Now, f of x. Okay, so we have a g, f of x is x squared, right? So now we got a g of x squared. This is a g of x. This is a g of x, right? This is g of x. That's the rule. When we have x squared in the place of x, we say x is just a placeholder. It just holds a place. When g of x squared is being called for, what do? You're going to replace the x everywhere where you had x by x squared. So 2x minus 1 will turn to 2x squared minus 1. So as a result, you have this function. Do you follow me? So F composite G, G composite F, depending on the order, if they have this different order, will produce different functions. So order matters. Order matters. Do you guys follow me? So when we were doing F inverse, so in the case of a one-to-one function, in the case of one-to-one function, F and its inverse, okay? It's inverse F inverse. What we are doing here is F composite F inverse of X, and the other one F of inverse composite F X equals to X, where this X is from the domain. Okay, I just want to make sure this is from the domain of F inverse. Okay, because F inverse is the first rule that apply to X. So X must be from the domain of F inverse. The second X, even though they have the same name, they mean different things. F will belong to the domain of F. Any questions so far?
Do you think you can explain the top again?
Which top? Here?
Yeah, or like do another example for it.
Do you understand this example?
I'm trying to find out like how or why you put 2x minus 1 instead of g of x.
So let's see, where you had a question, I'm sorry, here?
Yeah, I'm trying to find out why you put 2x minus 1 inside gx squared.
Because the g of x is 2x minus 1.
Okay, yeah, that makes sense.
Okay, g of x is 2x minus 1. Okay, the
Okay.
way, go ahead.
No, I'm just agreeing. I'm saying okay.
You got it? Okay, so next, remember the machine thing I was building for you? Let's look at the machine's perspective. So, okay, now for F composite G, what it means is that we have this X, okay? And this X will get to apply the rule of G. And we get G of X. Okay, and G of X will be served as the input for F. And then it produces F of something, right? So whatever the input is that input over here. Are you guys with me?
Yeah.
Okay. The same thing is for G composite F. So it's about order. Order matters. Order matters. Order is very, very important. Okay. So X here. So on the second part, you can see X given to F, right? F is on X first. So F rule applies to X first. And then it produces an output. That output is F of X. And this f of x is going to be served as input and then give it to G, the G machine. It produces an output of G of something, right? G of f of x, because the input to G was f of x, therefore it's G of f of x. Is everybody with me? So these are the two different perspectives. So whichever one you remember, which one you don't remember, even if you don't remember anything, just try to understand this. Okay, along with its notation, you will be quizzed on. You'll be quizzed on. Okay, so now, do you guys see the perspective? Now let's come back to our inverse function idea. So if the function f is a 1-to-1 in its domain, its inverse, okay, in the case of a 1-to-1 function in its domain, and its inverse is f inverse, and this is always true. So please put them on your flashcards with all these accessories. Have you done that before? Have you done that already? Because we're going to continue to do this. We're going to continue. Any questions? You can send me private message if you don't feel comfortable to ask questions in front of everybody, or even though I encourage you to do so. All right, now let's look at some other functions we can find its inverse for, right? This function has inverse, right? This function has inverse. And this function, wait, what did I do here? Did I make a mistake here? So this should be x. Did I make a mess here? Did I? X raised to the power 3. This should be x power 3. Oh my God, I made a mistake. Domain is all real numbers for x raised to the power 3. Oh, terrible. Terrible, you guys. I made a mistake. I made a terrible mistake. Domain
Maybe
range.
it was copy pasting.
Right. And the domain range, this is all wrong. I'm so sorry that I hope this doesn't get to. Okay, x to the power 3. Yeah, the copy and paste, and then I forgot to change a certain part. Okay, I forgot to change certain part. I also made a wrong statement. I just realized. I was telling you since yesterday that y equals to 1 over x is the only function that has its inverse is the same as itself. And I just realized that statement is wrong. Oh my God. You should have a good laugh, because I think this function's inverse is also exactly the same as itself. Okay, so let's look at this function. This function has inverse. The inverse is itself. Okay. Oh, well, so I need to make that correction. So you should have a good laugh. All right. It's not very good. I made that mistake. Okay, but anyway, I made a mistake. I declare that this function is the only function whose inverse is the same as itself. That's not true. Okay. And because this other function, y equals to x, and this function's inverse is also the same as itself. Okay, I apologize for that. All right, next it comes to continue. Oh no, what's going on? Okay. Next, let's look at these functions. What's going on? The software is not collaborating. What's wrong with you guys? You guys know these curve, right? Let me just.
They're increasing.
This doesn't show up. I think the software has a little hiccup. That's not a big deal. So I'm going to just add item 2 to the power x. Okay. Sometimes these software just have some hiccups. I don't know if what happened. I have no idea. It's okay, we fix it. I will fix it. But anyway, now look at these functions. We're about to introduce logarithm. But anyway, so that are compositional functions, right? That's compositional functions. Now, I'm going to make a couple of statements, okay? Carefully examine my statement, okay? I encourage you, all of you do that, because sometimes I do say something wrong, and later I will regret. But as soon as I discover I made a mistake, I will correct, okay? Now, we talk about that if a function is an increasing function, in its domain, it is a one-to-one function. Do you remember that?
Yeah.
Okay. Now, for every one-to-one function, we just talked about every one-to-one function has an inverse, right? Every one-to-one function has an inverse. And the inverse is unique. Each one of these functions in the table right now, they are what? They are increasing functions, aren't they? So each one of them is what? One-to-one. And if they are one-to-one, they have what? Each one of them has an inverse. Okay? Each one of them has an inverse. And now we're going to take 2 to the power x, for example. Okay, so now we're going to do one at a time. 2 to the power x. 2 to the power x is an increasing function. Therefore, it is a one-to-one function. Can I say that? Thus, it has exactly one inverse. So let's find its inverse. Let's find its inverse. Okay, how do we find inverse? Yesterday we talked about that 2 steps, right? Y equals to 2 to the power x. How do we find inverse for that?
Swap
What is the
the
first
X and
step?
Y. Swap the X and Y.
Swap x and y. So we got x equals to 2 to the power y. And then what?
Solve for Y.
Solve for y. And what do we get? If you solve for y, what you get? We got a y equals to log base 2 of x. Logarithm. How many of you still remember a little bit thing about logarithm?
I'm the one also.
You're Farouz is the only person?
I haven't seen one in about 4 years.
That's
I
okay.
seen it, but I forgot how to convert it back.
I'm sorry?
I've seen it before, but I forgot how to convert it back. And then back to
No problem. I'm here for you. Okay. Whether you had it 4 years ago, 10 years ago, we're going to bring you together. Right. But whenever you have questions, please let me know. Okay. So let's bring these two together. Okay. So we're going to see the definition. You can see that there's a lot of interesting facts along the process, right? Y is equals to that. Okay. 2 to the power of y. If 2 to the power of y equals to x, then y is log base 2 of x. This is one of the cases in the example of the definition of logarithm. I'm going to give you the general definition of logarithm. Okay. The general definition of logarithm goes like this. Log base of b. Okay. Omega equals to triangle. I just use any symbol, okay? That takes my fancy. If and only if b raised to the power of triangle is equals to omega. Sometimes I like to call omega bologna. Okay, and we have some a specific requirement for the base. The base b must be larger than 0. Not equals to 1. When did I mention this condition before? In this class, last week. When did we mention this condition before? When we introduce exponential function, right?
Yes.
Recall exponential. We say exponential function is a family of function. Okay, it's a family of functions. And they all look like this. B raised to the power x, right? Where B must satisfy this condition. And logarithm function also must satisfy that same condition for base. Now, this is the general definition. Okay, if you find this a little bit overwhelming, no problem. Okay, I'm going to try to get you understand this using this example. Okay, so let's get started. So now we're going to bring this together. Okay, we're going to bring this to, is this a special case? So this is the special case. Okay, special case. The special case when the base is 2. Let's see how this works. Let's see how this works. Okay, now 2 to the power of y. There's a domain consideration here, isn't it? Do we have a domain consideration? Right? So now I'm going to change the symbol around a little bit. Okay, I'm going to call this triangle. And I'm going to call this baloney. All right. So this is going to be triangle. And this is going to be the baloney. Does everybody follow me? We're going to try to understand logarithm. I'm going to review logarithm. Everybody have paper pencil with you, please. So in this general definition, which is for any base, if we replace b by 2, what do we get? If we replace b by 2, what do we get? That's what we get, right? Which is exactly this one. It's just in different order, right? You guys see that?
Mm-hmm.
So I'm going to just bring it to the same, just bring it here so that they're even in the same order. Is that good? Does that help? Yes? Do you see they're exactly the same? Because B is already 2, so we don't need to. And of course, these just change of orders, right? It should make no difference. Is everybody with me? We're going to come back to the function, to the inverse function perspective after we reviewed about logarithm. Okay, so since this box is the same as this guy, so I'm just going to remove this guy. Okay, next, what does it mean? We are very familiar with logarithm, don't we? We're very familiar with exponential, right? We did it, didn't we? Do we still remember the exponential table we did for 2 to the power x? Let's do it again. 2 to the power x. Did we make that table?
Yeah.
Forget about table, right? One of the cases, we say, hey, 2 to the power of 0 equals what? 1. Yes?
Yes.
If 2 to the power 0 equals to 1, in the place of triangle, it's 0. So this is 0. So this is 1. So logarithm just saying this 0, this number triangle powered the base is equals to this number. You just write number in different ways. But this way you emphasize the exponent, and this way you emphasize the power. Do you guys follow me? So this is saying if you say 2 to the power 0 equals 1, that's the same thing as saying log base 2 of 1 is equal to 0. Okay, so the log function is introduced to express, to emphasize power, the exponent alone. Does everybody follow me?
Yes.
Let's practice a few more. Let's practice a few more, okay? I want you to work from the right to the left, okay? To the power of 1, what does 2 to the power of 1 equal to? 2
Equals 2.
3.
Did you say that? No.
So now I want you to put these other numbers in place. I give you the number for the triangle place. And you're gonna put these numbers, you're gonna find out this number and put it in the proper place on the left. Can you do that?
Yeah.
Okay, please do it. Thank you. Bruce, you have any comment?
Do you want me to do it for you right now?
Yes, please.
Okay.
I want you to complete
for the-
this.
For the one that you're on right now,
Right. You see,
mm,
hello, everybody. Okay, maybe I'm not dramatic enough, huh?
so omega is equal to 2.
2 to the power of 1 equals to something. And that something is going to be in the place of omega
Yes.
or bologna. And 2 to the power of 1, that 1 should go somewhere on the other side.
It's gonna go into the
Okay, so I want you to
Theta.
complete this guy, complete this guy, complete this guy, complete this guy. Can you do that for me?
Yeah.
And you
Okay.
tell me what that logarithm does for you.
Would the first one be log base 2 of 2 equal 1?
Perfect. Perfect. So basically, we're saying there's another way to say it. In other words, 2 to the power 1 is 2. In other words, that log base 2 of 2 is 1. You hear me?
Yes.
2 to the power of 2 is 4. In the other words, 2 to the power, log base 2 of 4 is 2. You follow me? So the introduction of logarithm is really the exponential function spoken in the other words. You follow me?
Mm-hmm.
And the last one, 2 to the power 3, what does that equal to?
8.
8.
Therefore, it would be log base 8 equals 3.
Log base 2 of 8.
Oh, I forgot to do my bad.
The log base 2 of 8 is
3.
3. So what does the logarithm express? Logarithm express exponent specifically. You get it?
So Professor, if you have an unknown variable in the exponent using the logarithm property, we can bring it down and get the answer.
Yep. That's right. Okay, we're going to see that. We're going to see that. Okay. The next example, we're kind of approach this kind of slowly, but I'm going to give you some interesting perspective here. Okay. You know, in Los Angeles, we often have earthquakes, right? And how is an earthquake measured? It's called Richter scale, right? Richter scale, right?
Yeah.
The Richter scale has something to do with logarithm. Okay, now let's change a base 10. Let's change a base 10. Okay, change to base 10. So this time I'm going to choose a base 10. Okay, so I don't need this anymore. So I'm going to put a 10 here, 10 here. When we have a base 10, we actually could use just log. So when you use the symbol log, log, by default, the base is not indicated. It means common log. Why it is called common log? Because its common log is often used in scientific calculation and is often used in most of the calculators. That's why it's called common log. Okay, and it's also used in the earthquake measurement. For example, okay, I want you guys to do a couple of things. Just practice using this definition, okay? Suppose I put 0 here. Okay, gonna do the same thing. Are you guys with me?
Mm-hmm.
Okay, you're gonna complete the other side. Does everybody know what to do? In the other words, right? In the other words.
Professor, looks like a good quiz question type questions.
Oh yeah, I'll be quizzing you about these things. Of course, easy to make these quizzes, right?
So by practice, we can master all these concepts.
That's right. Someone about to say something. Jacob, you gonna say something, Jake?
No, I just wanted to say for the first one, would it just be log base 10, 1 equals 10? Or am I wrong on that? For the 0.
Which one you're talking about? This one?
No, for the 0. For 0.
For the 0. When you have a log, the base is not indicated, you can just say log blah, blah, blah. You don't have to mention the base.
Okay, so it'd just be log 1 equals 10, right?
Log 1 is equal to what?
10.
Think.
Oh, no, it's 0. It's 0. My bad. It's 0.
That's right. You got it. I love it. Self-correction is the best. Okay. Do you guys follow me? Follow us?
Yeah.
10 to the power 0 is equals to 1. In the other words, log 1 is 0. Listen to what I say, okay? I did not mention the base because it's a base 10 is a common log, so it's kind of just, it's a simplified version of it. Okay, any other base, we must indicate the base. Okay, so when you write log, by default, base is 10. All right, so now 10 to the power 1 equals to what? 10, right?
10.
So what is on the other side?
10 replaces the omega. It's log
10 10
equals
is
1.
1. Log 10 is 1. That's how you say it. Okay. Log 10 is 1. Log 10 is the same as 1. Can we speak it? We have to be able to speak it, right? How about the third one? Right?
Yeah, log 100 equals 2.
Log 100 is 2. Wonderful. You got it. How about the next one?
Log, sorry, log 1000 equals 3.
Perfect. That's it. Now, suppose that the magnitude of an earthquake, okay, the power, okay, oftentimes the power is measured by something to certain power, right? Something certain power. So 10, suppose we say magnitude earthquake of 3, Richter scale will be after the power of the earthquake being taken common log. So if you look at the log of 100, log 1000, suppose 1000 is the power of the earthquake and 100 is the power of another earthquake. If we only look at 2 and 3, and 2 and 3 will be the reported Richter scale, the actual power of the earthquake actually is 10 times different. The power, the Richter scale may be different by just 1, right? From 2 to 3. But the actual power of the earthquake is different by 10 times. Does that make sense?
Mm-hmm.
So this is how the common logarithm is used in the earthquake measurement. So instead of saying that big number, right? Okay, if the earthquake is what is the strongest earthquake you have experienced? The strongest earthquake I experienced was the Northridge earthquake, right? It was 6 something, right? That is about log 6 zeros. That's the magnitude. But this is the power of the earthquake. And this is what? This is the Richter scale. So the Richter scale is after taking common log. Make sense? Does that make sense?
Yes, Professor. For example, if you had a small earthquake size like 3, how would be that compared with 6?
Yeah. Or earthquake 7, Richter scale 7, right? Richter scale of 6 is pretty powerful. Richter scale of 7 is 10 times stronger. That makes sense? Does that make
Yes.
sense?
Yes.
Okay, so that's logarithm. That's logarithm. So next, we're gonna work more on base 2. We're gonna work more on base 2. Okay, as we work more on base 2, I want you guys to practice logarithm. Okay, I want you guys to practice logarithm. So next, I'm gonna make a table because we're gonna figure out this function, log base 2 of x, right? If this is a rule of a function, what's the domain, range, x-intercept, y-intercept, and so on and so forth? Do you follow me? Yes? Now, so you're gonna work with me, okay? We might have to do a breakout sessions. New rule, okay? And you can see this new rule is closely related to an old rule, exponential function. Do you guys see that? So the rule is a little bit more complicated. Do you guys see that? Now recall the definition of function. A function is a rule. Yeah? And this is the new rule. X, the input, log base 2x. Okay, I'm going to give you some input. Okay, the first input I'm going to give you is 1. The second input I'm going to give you is 2. The next input I'm going to give you is 4. The next one, 16. Okay, and I'm going to give you half. Okay. Let's start with these two. These 1, 2, 3, 4, 5. If the input is 1, log base 2, 1 equals what? We just did it, right? What would that be?
Zero.
That's right. When input is 1, output is 0. Input, output. New rule. We got a new rule, everybody. Remember the theme of this course is a function. We are learning another rule. This is number 10. This is number 10 on the table. Now, the input was 1. Input, how about input was 2?
1.
Excellent. So when input is 2, output is 1, right? What if input is 4?
2.
2. Excellent. So when input is 4, output is 2. Input is 16.
Four.
4. Wonderful. You got it. 16, 4. Okay. So how do you know you get it right? Well, all you have to do is just to check if this is 0 power 2, it should equals to 1. This 1 power 2 should equals to 2. This 2 power 2 should equals to 4. Do you guys follow me? This is 4 power 2 should be equals to 16. Yes? You follow me?
Mm-hmm.
I have another trick to show you. You see, log base 2 of 2, 2 of 2, 2 of power 1, this number is the same as this number. Do you guys see that? Yes? This 1 is 2 to the power 0. And the answer is 0. So when this base is the same as the log base, when the log base is the same as the exponential base, you just bring down the number. Do you guys see that?
Yeah.
And this is 2 squared, isn't it? 2 power 2 is 2 power 2, right? So 16 is 2 to the power 4. So it equals to 4, right? Did you guys see that? That's a little trick. Well, it's also one of the properties. Do you guys see that?
Yeah.
Now I start to give you some numbers that's gonna take a little bit more effort. How about half? The input is half. How about quarter? Everybody must try to do this, okay? Whether you get it or not, I'm not coming into your house to check on you, but you must make the effort. It will benefit you. If you have any question, please don't hesitate to ask.
I call it, Professor, real-time questions.
Hmm.
Real time, right now. If you have question, ask it right now, then waiting for next day or next week, just ask it real time right now. That's the professor trying to remind.
Thank you, Farouz.
You're welcome.
This is also the advantage of doing live lectures, right? Because you can see I already have lots of lectures in recording.
That is true. That is true. I remember you said some of you may not be here yesterday, so they can watch the recorded, but in the recorded they have no choice to ask real-time question if they have question. But
That's
live,
right.
you have chance. Why not ask question if you have?
Yep.
for the 1/2, would it be -1?
Sorry?
Would it be -1?
Yes. Good job. Yes. Because -1 power 2 is 2 to the power -1. 2 to the power 1 is half, right? So half 2 to the power -1 is very useful, isn't it? Wonderful. Aren't you proud of yourself? You figured that out? Give yourself a pat on the back. Because we're doing these and it gets a little bit harder and harder, okay? Now, for each one of these input, we have a unique output, and we put the input output together. Any questions, you guys? When input is half, the output is -1. Now, 1/4, 1/8, and then you get to 0, -1. Hmm? You're gonna have lots of homework today.
It's √-2 is equals to
Wonderful, wonderful. Because 1/4 is what? It's 2 to the power -2. You see the advantage of using negative exponents in the case of fractions, right?
Mhm.
Great job. Any questions so far?
No, not yet.
Okay, keep going.
So
You're doing
power-
great. You guys are
power of
doing
-3.
amazing. Sorry,
The power of -3.
the answer is -3, right?
Yeah, -3.
So this is 2 to the power -3, right? So -3 power 2 is 2 to the power -3. You see, it's very easy to check your answers, right? So the input output there. So now we got a 1/8, comma -3. How about 0? How about -1? What's going to happen?
This is the area why we need to know the domain, Professor.
Yep. Have you found a number such that that number power 2 is going to give you 0? That's what you're looking for, right? We're trying to find a number. That number power 2 to the power of that number you're looking for must be 0. That would be the answer. What is that answer? In other words, we're applying this rule. We're applying this rule, and the input is, this is the input, right? There's this rule that produces output. When the input is 0, what happens? What will be the output? What is that unique output that we should expect? And what is it? If that output exists, okay, suppose it's called heart. No, not heart. What name should it be? I'm gonna give it a very special name, spade, right? The spade power 2, 2 to the power of the spade should equal to 0. What is that spade? Have you found it? Have we found it?
Does it not exist?
That's right. Wonderful. Doesn't exist. So for this input, there's no exactly one, there's no output. For this input is 0, there's no output. Therefore, this input is not qualified to be in the domain. You follow me?
Mhm.
For input to be qualified in the domain, that input must guarantee there's exactly one output. If there is an input does not produce any output, and that input should not be in the domain. Do you follow me? So all these domain things, domain and range, they're totally defined by this function definition. This is the definition we have introduced at the beginning of the semester. Very, very powerful definition. It says a lot of things about a lot of things we do. Okay, you all trace back to that definition. All trace back to that definition. So this doesn't exist, right? Does not exist. But we also have a very powerful statement we have used before. When we talk about the domain and when we talk about the range of 2 to the power x, what did we say? That one sentence statement. What do we say about 2 to the power x? In terms of range. What is that narrative? We have that one sentence statement about the domain and range in one sentence. What did we say about 2 to the power x? Isn't that here?
Two to the power of x is greater than 0 for all values of x.
That's right. That statement already tells us. That statement already tells us what? You want to find 2 to the power something equals 0, it's not going to happen. It's never going to happen, not in a million years. You follow me? This statement, that one sentence statement, is very powerful. Very powerful. You will find yourself using it many, many times over. Okay, that's why I insist that you have that one sentence statement, because it can be used very powerfully in your statements. Because it's a true statement, isn't it? It's a true statement. Okay, so 2 to the power x is greater than 0 what? For any real number what? X. Okay. Oops. All right. So this one has no, the other narrative would be saying what? There's no solution. So this is impossible. Impossible. Such state does not exist. You follow me? But the top is sufficient. Okay, it's sufficient. So there's no definition. So 0 is not in domain. Okay, and this is undefined. Undefined. So if something is undefined, we don't even write it. You will see this in calculus class. If a function is not defined there, we don't even use the notation. Okay, so then we say this is undefined. Undefined. And as a result, 0 not in domain. How about -1? What if the input is -1?
Wouldn't it also be undefined?
Exactly. Wonderful. Because 2 to the power x is always positive. It can never be less than 0. It can never be 0. Therefore, this is also undefined. Do you guys follow me? You got it. In fact, the domain does not include any number 0 or less. Will the domain include all the positive number?
Yes.
The answer is yes, because for every positive number, we can find exactly one output. So now I want you to read the definition of function one more time for me. That definition applies to this new rule. That's the power of definition. Okay, when I was in college, just one of those days, I realized the power of definition. I was just so amazed. I was so amazed. There was a moment that I felt, wow. I don't know if you start to feel that way. I hope you will feel that way someday. Well, you probably have felt that now, right? After how many functions we have studied? 1, 2, 3, 4, 14, 15, right? This is the new rule, right? Every function has to be fitting. Every function has to be fitting to that definition. And we just talked about it at the beginning of the class. How many do we have? How many functions do we have? Infinite. As many as you wish. But all of those is described by that one sentence statement. Isn't that powerful? What? Right? We say some words are golden, right? These words are golden because if you remove any one word, it's not going to work. If you add one more word, it's redundant. It's just right. Just enough. Not too much, not too few. Okay, so without further ado, so what do we say about the domain of log base 2x? What's the domain? What will be the domain? Let me put it here then. Larger than 0. All the positive real numbers. All the positive real numbers. 0 to infinity. Correct. Very good job. Very good job, Andre. Okay, so next, shall we plot the points? As we always do, right? For this new rule, let's plot points. I'm going to plot all of these points. Okay. Everybody, please roll up your sleeves. Have you guys started? So for this new rule, we're going to plot points. Okay, we have 7 minutes left. So let's try to get this done just a little bit faster. Okay, so 1/8, comma, -3, red dot, 1/4, -2, 1/2, -1, input output, 1, 0, 1, 2, 1, 2 input, output 1, 4 input, 2 output. I didn't do the 16 input 16. Okay, you can ignore that. Okay, now shall we connect the dots? Log base 2 x. That's the log base 2 curve. That's the log base 2 curve. On this curve, look at there's 2 directions, right? Domain does not include 0. So the input can be any number larger than 0, so that any number can be as close to 0 as possible. You guys see that? The closer we're to the input is to 0, what happened to the output? What happened to the output? You guys see that? Do you see that?
Mm-hmm.
What can we say about that phenomena? X is approaching 0 from larger than 0, positive, okay? Log base 2, you know what? The software doesn't have enough good notation, so I'm going to write it in a better notation, okay? So let's do this. Okay, so this picture, what does it tell us? Right? When X is approaching 0 from larger than 0, okay, which means what? You guys are gonna need this You guys gonna need this in Cal, okay? When x is approaching 0 from larger than 0, that's the input, horizontal, right? Approaching 0, as close as possible. The output is vertical. You guys see that? The output, log base 2 of x approaches negative infinity. You follow me? And of course, when x approaching positive infinity, log base 2 approaches positive infinity. Okay, that's obvious on the other side. Is it increasing, decreasing, 1 to 1? Yes or no? May I leave for a second? No problem, no problem. We'll have a recording ready for you. All right? All right. Is this an increasing function? Obviously, right? Obviously. What's the x-intercept? What's the y-intercept? Shall we summarize? Would you like to summarize? Would you like to summarize?
There's no y, but there is one x.
That's right, there's no y-intercept. So the curve will never touch y-axis, right? Because to touch y-axis, x has to be 0, remember? And x cannot be 0, right?
Yeah.
Right? So we have a 1 x-intercept, but we don't have y-intercept. Okay? And what else have you seen from our discussions with functions? We have much experience before, right? The first 8 function, and then the exponential function. Now is the log function base 2. What else do we see?
That this is a one-to-one function.
I'm sorry?
That this is a one-to-one function.
This is a one-to-one function. It's an increasing function. Yes, absolutely.
Professor, summarizing it, as you mentioned, give us a chance to create our flashcard if we choose to.
Yes, but this time today, I'm going to leave that summary for you. We're going to do it tomorrow morning together. But I want you to try to do the summary today. Okay? Could you do that? Because I know you can. And tomorrow we're going to bring all our solutions together and we're going to discuss, and I will give you some homework. Okay, you're going to get some homework on the logarithm. Okay, and you do the summary. Okay. I'll see you guys tomorrow.
Thank you, Professor.
Great job. Great job. Wonderful. A great
you, Professor.
participation today. Okay. And I really enjoy this process. If you have any question, please, any question, reach out to me. Reach out to me. Okay. Great job.
Thank you.
Thank you.
Thank you. I'll see you tomorrow.
I'll see you guys tomorrow. Do this and try to do summary this time yourself. Okay. You can do it.